This is the example 3.1. As you may see, this example have the specimen shown here. It has the gate length of 50 millimeter and has the initial diameter of 12.5. This steel alloy specimen put into this tensile test machine, and we are trying to draw the stress strain diagram of this specimen. After that, we determine the modulus of elasticity, the proportional stress, modulus of resilience, and yielding stress. And finally, we determine the ultimate stress and fractional stress. Let me recall again the TIS, the Thai Industrial Standard, when they specify the specification of the steel. We supposed to check the yielding stress, the ultimate stress, and the modulus of elasticity of the material. The problem gives us the raw data of the load as shown here, the elongation and the area. Actually, the area we can determine from the diameter given in the previous slide. So the normal stress is the load divided by the area. So we got the stress as shown here. For the strain, we have the longitudinal here, and then divided by gate length, and we obtain the data for the strain shown here. The stress is going to be the vertical direction, the strain going to be the horizontal direction. So we put this data into the Excel, and then we get the graph. The first graph is this one, the brown curve, that's based on the rough scale, and the second is the dot blue curve, that's based on the finer scale. And as you may see, the ratio of this 0.1 and 0.002 is going to be about 50 times. This graph is important because it's going to provide us with the modulus of elasticity. And since the material has no yielding stress, we also going to use 0.2% offset to determine the yielding stress. So the phi scale graph is important for us to determine those yielding stress and the modulus of elasticity. Okay, for the graph, let us start by finding the modulus of elasticity. Okay, when we consider the finer scale and determine the slope of the graph, I recommend you to mark the no value of the strain, and then you may draw it up to find the stress. So let me mark the strain at 0.001 and put the vertical line to determine the normal stress. By doing this, sometimes you got to do the proportion. Let's say if the distance between here and here, let's say it's going to be, by using your ruler, 20 centimeter. Okay, and if this is going to be 20 millimeter, okay, and this is going to be 4 millimeter for the proportion you may have, like 20 centimeter for 100, okay, and then if you have 4, this is going to be 4 times 100, and then divided by 20. What you get, that's 400 divided by 20 is going to be about 20 here. So if you practice with the 200, so the value here going to be 220 megapascal. So the height of this is 200 megapascal, and the horizontal line is going to be 0.01. So the modulus of elasticity is going to be 220 divided by 0.001 is 220 gigapascal. And next, for the proportional limit, you put the ruler along the straight line here, and then you mark the line, and when the straight line separate from the curve, you're going to get the proportional stress. So it's going to be about this point. This is 200, right? This is going to be 250, and those is 300. So it's just above 250. You may estimate it's to be 255 if you like, or you do the same proportion. You may get sigma's proportional limit of 225. For the next, modulus of resilience, U sub R, is the area under the stress strain diagram, which is corresponding to the proportional limit. So you have proportional stress already, so you got to find the proportional strain. Just put the line down there. You got the proportional strain of 0.0012. So the area of triangle under the stress strain diagram is going to be the modulus of resilience of this material. So it's going to be 1/2 of 255 times 0.0012, and you get it for 0.153 megajoule per cubic meter. Let me clean up about the unit of this. For the megapascal, it's going to be 10 power 6 Newton per square meter. Okay, and for millimeter per millimeter, it can be also meter by meter. So when you times it, this one gonna be 10 power 6 of Newton times meter and divided by cubic meter. What is Newton meter? Newton meter is the joule. Why? Why Newton is joule? Because work is force times the distance. That's the force move. Okay, so force is Newton, the distance is meter, so you get Newton meter as the joule. So 10 power 6 is million, so it's going to be million joule per cubic meter. The last one, summation of F sub y. You cannot read during stress directly from the stress strain curve. This material have no stress strain curve, so you got to mark 0% offset. 0% offset is going to be 0.002, and you have 0.02 here. You got to mark it up, okay, to this point also. the point of 0.02, and then you mark the line parallel to the linear region. Okay, and when it hit there, you just project it over here. This is 300, this is 350. Okay, you do proportion, you get it 335. And for the ultimate stress and fractional stress, you can use the log scale to get the highest point of the stress. This is important to get according to the Thai industrial standard, okay, such as the same as this one and the same as this one. So for the fracture stress, you may get it what? This is 400, this is 450, this is 500. Okay, you may do the proportion is maybe 475 or 480. Okay, next, after we get the mechanical property, we are going to use that mechanical property to determine the deformation of a structural member. Consider the member ABC, which is the two force member. Okay, is subjected to the tensile force of 68 kilonewton. Force is 68 kilonewton, and we are going to take a look how it's going to deform, how large the elongation of the rod is. Okay, and then we just release the force of 68 kilonewton, and then we determine whether the rod is going to return its original. The rod going to return to the original if both AB and BC has the elastic behavior. If not, what the permanent set. So it's up to the behavior of the section AB and BC. If they both are elastic, when you release the force, they're going to go to the same length of 500 millimeter and 400 millimeter. If both of them plastic, okay, both of them going to have the permanent set. If one of them has the plastic behavior, so only that one has permanent set. That's the concept of this. And from the ending static, the member ABC also can determine from some type of structure if it's required. Okay, let's see this. Okay, after you cut this portion, you may draw the free body diagram of this portion, and you may determine the internal force of this portion to be both of 68. Okay, this is 68 kilonewton. When you cut this and then you use the equation of equilibrium, you may determine the force F sub AB to be 68 kilonewton. Also, if you cut this one and you draw the free body diagram of this portion, and you may get the same thing. The force over here is 68 kilonewton. So the internal force here, that's going to be F sub BC, is also going to be 68 kilonewton. So all the internal forces is going to be 68 kilonewton. So for the section AB, we have this one for diameter of 20 millimeter. So the area going to be pi, and this is 0.01 or 10 millimeter square. We have the stress here less than sigma sub y, so this one gonna have the elastic behavior. The next one, this small portion, okay, after we cut it and we determine the internal force of 68 kilonewton, and we divide it with pi radius square. The diameter is 15 millimeter. The radius is 7.5 millimeter and is 0.0075 meters square. And this is going to be larger than sigma square. So we conclude that the portion of AB is elastic behavior. The portion BC is in plastic behavior. Oh, okay. Since the AB is in the linear elastic behavior, the strain can be computed using the Hooke's law. Hooke's law sigma equal to E and epsilon. So the epsilon is sigma divided by E. The E we have is for 220 gigapascal. So it's 220 10 power 9 pascal. And stress is 216.5 10 power 6. So this is cut and this is reduced to 10 power 3. We get the strain of 0.0009841 or 0.9841 10 minus 3 millimeter per millimeter. This is the linear elastic strain. And for the friction BC is the plastic behavior. So you got to use the diagram to determine the value of the strain of the section BC. So go back to the stress strain diagram and we have the stress of 384.8. Okay, as we have here, the stress is here. We put the 384.8 into the vertical direction and project horizontally to hit the graph. Okay, and project it back, and then you may estimate the strain here to be 0.0108. It's not 0.011. Okay, 0.011 is here. It's very close to. You do the proportion, you get this 1.0108. This is going to be the strength of the portion of BC. So we have the strain BC very big due to the plastic behavior. The strain AB is very small, okay, due to elastic behavior. And then we have strain equal to deformation divided by L. So the deformation gonna be elongation per se, maybe the strain times L. So you put both for its original length of 500 gonna times this. Okay, then 400 gonna times this one. You get the length of 408. So now the total length gonna be 904.8 millimeter. You start by 900 and then you L palm is going to be 904.8. And then you release the force. When you release the force, you can see that this portion has elastic behavior. All the deformation that occur here gonna return back. So only this part going to have some permanent set. Okay, only BC. Going to the graph again, this time when you release the force, the curve gonna return by strain hardening effects. And you know that this is the height of 384.8. Okay, and then you have E. The modulus of elasticity is equal to sigma times epsilon, and this time you take the epsilon up, so the epsilon is gonna be stress is here is the stress divided by E. Okay, to be the strain over here, which is the strain recovery. This is the strain that is going to return back. So put it over there. The stress is 384.8 times 10 power 6 divided modulus of elasticity is 220 times 10 power 9. So it's going to return by 0.00178. So we have at this point, this is the strain of the BC, and it's returned by 0.00175. So the permanent set is gonna be taking this red one minus with this blue one, and then you get the result of 0.00905. So this is gonna be the permanent set. And then the BC is 400 millimeter. So you times the strain with 400 millimeter, you get the permanent set of 3.6 millimeter. So the new L is going to be 900, okay, and 0.36 millimeter. Let me conclude that we start with 900 millimeter ABC member, and then under the 68 kilonewton is going to be 900.48, and when you release the force, it's going to be 900.36. So 900, sorry, it's going to be, this is not correct, it's going to be 903, okay, and then 0.6, it's going to be 903.6, not this one, it's going to be 903.6, 900 to 904.8 and 903.6. Okay, for the second example, we consider the column of structure, and I will put it in the new clips. Okay, so the first example of chapter 4 supposed to be in here.